So in this video, we're going to talk about finding the tangential bending stresses in a curved beam. So these are the stresses due to an applied bending moment. Okay, and it's typically been denoted as a normal stress, typically sigma theta. Okay, so to calculate sigma theta, we need to know a few things about our beam, our curved beam and bending. Okay, the first thing we need to know is we need to know the location of the neutral axis. Okay, so at the neutral axis, the stress due to bending is 0. So our neutral axis we'll denote with our letter Rn. Okay. The second thing we need to, I guess we'll define here is overall in our system we have the radius from the center of our curvature to any point within our beam will be denoted with R. The angle relative to the center of our beam we can denote with the angle theta. And then the change in the angle we can denote with a d theta. Okay. Um, so if we look at a particular cross section, so if we take a section cut and we just look at the cross section within that area, okay, um, we can define all our variables on our cross section. So we still have our neutral axis here. Okay, we have our radius r. All right, we have the radius to the neutral axis Rn. All right, we have the radius to the centroid Rc. All right, and then we have our centroid of our section. All right, and then we have a distance from our centroid to our point of interest, or from our neutral axis to our point of interest, which we can denote with the letter y. Um, and then the last thing I'm going to define here is we have something called our eccentricity, which we'll denote with the letter E, which would just be equal to RC minus Rn. Okay? All right. So, using these definitions, we can determine a few things about our section. So the first thing we can do is we can determine what is our strain in a theta direction. Okay, so if we look at a small section of our curve section here, okay, and let's say we have 2 points, point A and point B. All right, we know that the length from point A to point B would be equal to r times theta, where theta would be in radians. Okay, all right, so that's our arc length on the bottom. Okay, and then the change in arc length is going to be dependent on the location y. All right, um, times d theta. Okay, so d theta is a very, very small angle, right, and y is just equal to the distance from the neutral axis to the point of interest on our section. Okay, so um, so now we have a definite equation for strain. We know that normal stress we can relate to strain using Young's modulus. So if you just plug in um, uh, our E theta equation here, we end up with this equation here, right? And then we know that that since this is considered pure bending, we know that there has to be no axial force in our system. Okay, so because there's no axial force in our system, we know we can integrate um, our area. We're just going to plug in our sigma term here. All right, so we're just going to plug in our minus E Rn minus R divided by R d theta theta times dA. Okay, And then we can bring out all of our terms that aren't functions of dA. Okay, so we can bring out e d theta and theta from this equation, and we end up getting an equation that would be equal to Rn minus R times dA. Okay, so if we go to the next page, all right, we're just gonna take this equation here, and we're gonna divide both of the Rn and the negative R terms by R, and we'll distribute our integral. We'll break our integral into two separate integrals. Okay, so we can treat e d theta um, over theta as a constant, and so it's not equal to 0. So we can multiply both sides by theta over e d theta, and they'll all cancel out. So we're left with this integral here has to be equal to 0. So if we divide by r for both terms, we'll get this equation here for Rn, which is a constant, would be times the integral of dA over r minus the integral of just dA, which is just going to equal to negative a, must be equal to 0. So we can define that the radius to our neutral axis must be equal to this equation here, where it's equal to the total area divided by the integral of dA over r. Okay, so you're probably wondering, how do I solve for the integral of dA over r? You can use you don't have to worry about it. You can actually just use table 5.6.1, which should be located later on in the lecture. So that's on page 265 and page 266. Okay, they have, for each of these different cross sections, they have developed the integrals for these common cross sections for the integral of dA over r. Okay, so 255 and 256. All right. So the key things for curved beams um, is that unlike for a straight beam, your neutral axis will not be at the same point as your centroid. All right. And then for curved beams, your radius to your neutral axis is going to be less than your distance to the centroid.